Okay, so yesterday we discussed about the density of state. Okay, so those density of states we'll use in Debye model. Okay, when we'll calculate the lattice specific heat, and same time those density of states also will be used when we take the free electron theory of solids. Okay, so today we are going to discuss thermal property of crystal lattice. Okay, thermal properties का मतलब क्या है? We are basically going to discuss how specific heat varies with temperature. Okay, so put the heading specific heat. What do you mean by specific heat? Specific heat क्या होती है?
The amount of heat required to raise the temperature by 1 degree Celsius. Mass of the substance.
Okay, so generally specific heat we define, okay, by dq upon dt. Okay, so if we are giving a system heat and dq and temperature just by dt, then the ratio of dq by dt is called your specific heat. Okay, so in order to increase, okay, so generally specific heat measure in moles, okay, per moles. Okay, so the energy, the heat, okay, the heat required to increase the temperature, by 1 degree Kelvin, okay, of 1 mole of, okay, for 1 mole. Okay, the heat required to increase the temperature by 1 K for 1 mole of substance. Okay, for 1 mole of substance is called your specific heat. Okay, now generally specific heats are two types, depending on the measurement. Okay, how you measure. One is your, पहला कौन सा है? Specific heat at constant volume. Okay, so that is called your CV. Okay, similarly specific heat at constant pressure. Okay, that is called your CP. Okay, so CV is theoretically more important. Okay, we'll see why. So specific heat at constant volume. Okay, so what is CV? Okay, so we know from the first law of thermodynamics, our dq is, okay, dq is, so CV is what? CV is basically your dq upon dt. Okay, dq upon dt at constant volume, and CP is your dq upon dt at constant pressure. Okay, so those things you might have studied your thermodynamics course. Okay, so if I take the first law of thermodynamics, it says the whatever energy you give, okay, that will be used to increase the internal energy and to do the work by the system. Okay, so now if I want to calculate the specific heat at constant volume, okay, so dq upon dt at constant volume will give me du upon dt at constant volume. So since volume is constant, so this term will become 0. Okay, so we can see the specific heat. Okay, specific heat is directly related with your energy. Okay, so if you can calculate the total energy of the system, okay, as a function of T, then you can just differentiate that function and you can get your specific heat. Okay, that's why this is the more important theoretically. Okay, so if you see CV and CP, okay, because when we for solid, the CV and CP, okay, CP minus CV, this is almost 0 at low temperature. Okay, because when you what is the difference between CP and CV? Can anybody explain me what is CP and what is CV exactly?
Capital R gas constant.
So when we are heating sample, okay, if we're keeping the volume constant, okay, then the amount of energy required to increase the temperature by 1 degree centigrade is your CV. Okay, for example, so we are discussing solid, but I'm giving example of a gas. Okay, so if we have a gas in a chamber, okay, in fixed volume, okay, and if you supply dq energy and it increases the temperature dt, okay, then dq upon dt, because the volume is constant, okay, that will be a CV. Similarly, if we keep the pressure constant, okay, suppose now here is one piston, here is gas, and we have one piston. On the top of this piston we apply a weight, okay, so now my pressure is constant, okay. Now if I supply energy, what will happen? The internal energy of the gas molecule will increase, as well as there will be work done by this gas, so volume will change, okay. So internal energy will also increase and volume also change, okay. Now in the case of solid, in low temperature, when you are giving energy to a system, तो क्या होगा, उसको वॉल्यूम तो चेंज होगा नहीं सॉलिड का, ओके. सो क्योंकि if it's low temperature, okay, so solid तो melt होगा नहीं. So what will happen at low temperature for solids, okay, your Cp and Cv are equivalent, both are equal, okay. So Cp is almost equal to Cv for solids, okay, at low temperature. ये point clear है?
Sir, can you once more repeat what you just told?
भाई अगर solid है, Cp और Cv में डिफरेंस क्या है? जैसे मैंने एक वॉल्यूम फिक्स कर दिया, अगर मैं सिस्टम का एनर्जी दे रहा हूँ तो उससे क्या होगा, वॉल्यूम तो चेंज होगा नहीं, ओके. अगर कंटेनर फिक्स कंटेनर है तो क्या होगा, उसका खाली इंटरनल एनर्जी चेंज होगा. नाउ नाउ अगर उसके अगर हम पिस्टन लगा दें, कांस्टेंट प्रेशर लगा दें, तो क्या होगा, कांस्टेंट प्रेशर पे वॉल्यूम भी चेंज होगा. So you'll get difference in Cp and Cv value, okay. Now if you have a solid, okay, और now solid को मैं constant pressure पे हीट कर रहा हूँ, सपोज मैंने एयर एनवायरनमेंट में यूज कर रहा हूँ, तो जो भी एटमॉस्फेरिक प्रेशर है उस प्रेशर पे इसको हीट कर रहा हूँ. अब ये मेल्ट नहीं हो रहा है, ओके. अगर मेल्ट नहीं हो रहा है तो क्या हो रहा है, इसका वॉल्यूम तो चेंज हो नहीं रहा है, ओके. जो भी एनर्जी दे रहा है उससे इंटरनल वो उसके इंटरनल एनर्जी में कन्वर्ट हो रहा है, ओके.
Yes, sir.
So that's why at low temperature your Cp and Cv are same, okay. So in general, if you may have studied in your thermodynamics course, Cp, the difference between Cp and Cv is given by 9 alpha square b Vt, okay. So where your alpha is what? Alpha is linear expansion coefficient. Alpha is what? Linear expansion coefficient. ओके. बी इज व्हाट? बी क्या होता है? बल्क मॉडुलस, ओके. वी इज वॉल्यूम एंड टी इज योर टेम्परेचर, ओके. सो नाउ स्पेसिफिक हीट जनरली फॉर एनी सॉलिड is not constant with temperature, okay. So if you see
what's the formula?
9 alpha square b Vt,
it's a relation that we should
between Cp and Cv,
okay.
Okay,
this is for solids.
This for general expression. ये तो पढ़ा होगा ना थर्मोडायनामिक्स में, निकाला होगा ना रिलेशन, तो ये तो बहुत इंपॉर्टेंट रिलेशन है Cp and Cv में,
ओके सर.
ओके.
अभी निकालूंगा, ठीक है.
So now if you see specific,
क्यों लिखा हुआ है रिलेशन?
नहीं, 9 alpha square b Vt, okay.
Yes sir.
Okay, so now if you see the specific heat of solid experimentally measure specific heat. हाँ बोलिए
सर. Cp मैंने Cv R मतलब आइडियल गैस के लिए होता है क्या?
आइडियल गैस के लिए होता है, ठीक है. So if I see the variation of specific heat, okay, per mole, okay, specific heat for molar specific heat with temperature, okay. So my graph will be something like this, okay. So at high temperature my specific heat, okay, regardless of any substance, okay, कोई भी मटेरियल हो, कोई भी सॉलिड हो, उसकी जो स्पेसिफिक हीट है दैट इज इक्वल टू 3R. इसको बोलते हैं Dulong-Petit लॉ, okay. So what is Dulong-Petit law. You can put the heading Dulong-Petit law. So Dulong-Petit law. Okay. So this law says the specific heat of all solids, the specific heat of all solids, okay, is equal to 3R at high temperatures. Okay. Now ये high temperature क्या है? That depends, अलग material के लिए अलग होता है. We'll see that one. Okay. So the specific heat of all solids is equal to 3R. For example, अगर मैं room temperature ले लूँ, तो अगर मैं suppose metal ले लूँ silver, तो अगर रूम टेम्परेचर पे उसका मैं स्पेसिफिक मेजर करूं, दैट विल कम 3R. फॉर एग्जांपल, इफ आई टेक डायमंड, ओके, देन आई हैव टू गो अप टू 2000 केल्विन. सो हायर क्या है, वो भी हर मेटेरियल के लिए डिफरेंट थिंग है, सब्सटेंस के लिए अलग अलग होगा. ओके. सो बट इन जनरल एट हायर टेम्परेचर ऑल द सॉलिड स्पेसिफिक हीट इज इक्वल टू 3R. ओके. वेयर व्हाट इज आर क्या बोलते हैं? व्हाट इज आर क्या होता है?
Gas constant.
गैस कांस्टेंट. ओके. ओके, इसकी वैल्यू क्या होती है? दिस वैल्यू इज 2 कैलोरी.
8.31.
I'm writing calories. Okay, 2 calories. Okay, per mole per Kelvin. Okay, per Kelvin degree. Okay, so you can multiply it by 4.18 and then it will become in joules. Okay, so now the CV is 3R. Okay, so 3R means it will be 6 calorie per mole per Kelvin. Okay, if you want to write in joules, okay, then you have to multiply by 4.18. Okay, so this will become almost 25 joules per mole per Kelvin. Okay, so this value is what you are, 25 joules per mole per Kelvin. Okay, so all the solids,
these values are fixed for all the.
these values are fixed for all the solids. Okay, at high
Okay,
सर
high
आपने किससे मल्टीप्लाई किया यहाँ जरा 6 का कन्वर्जन करके?
so 1 calorie is equal to 4.18 joules. Okay, ये रिलेशन होता है ना, 1 calorie.
हाँ हाँ got it.
Okay, so now if you see at low temperature, okay, at low temperature जो specific heat varies as a TQ by law. CV is proportional to TQ. Okay, so at T is equal to 0, okay, when T tends to 0, your CV tends to 0. Okay, and at low temperature it varies as a power, as a T power cube. Okay, but Dulong-Petit's law is only valid at higher temperatures. Okay, now we have to explain this graph. Okay, this variation of specific heat with temperature we have to explain. Okay, so
this is experimental graph.
This is the experimental graph. Okay,
Okay, sir.
so now,
Sir, can we say at higher temperatures also CP should be almost equal to CV, or
how
there will be some difference?
How at high temperature CP should be equal?
I mean, even at higher temperatures, pressure. If you pressurize, volume should
No,
not change.
so there will be, I gave you formula solid. So there was alpha. Alpha is what? Linear expansion coefficient. Okay, so generally in temperature, the expansion is very less. Okay, but if you give too much very high temperature, okay, then your solid will melt. Okay, then the alpha will be high. Then in that case it will be very high. Difference will be high. Okay.
Yeah. Okay, sir.
Okay. So now, so there are 3 models we are going to discuss, which will explain, okay, the variation of specific heat with temperature. Okay, so number 1 is classical model. Okay, number 2 is Einstein model. Okay, and number 3 is, which is this is a more accurate, that is Debye model. Okay, so what classical model says? Okay, so your classical model, okay, this model is basically based on equipartition of energy. Okay, based on equipartition okay, of energy, equipartition of energy law. Okay, okay, and what we assume.
Sir,
Uh-huh.
sir,
Hmm.
these three models
Hmm.
means tells about the relation between CV and T.
No, by using these three models, we are trying to explain the experimentally obtained curve of specific heat. Okay.
Okay, and different solids.
Different solids, of course, different solids. Our
Okay.
aim is to see the variation of specific with temperature. Okay. So in
Okay, sir.
classical model is based on equipartition law of energy. Okay. So in this, so what is equipartition law of energy?
Energy is equally distributed among all the degrees of freedom per
Okay.
molecule.
Okay. So जो
K
भी
by 2 kVT.
so सिस्टम को हम जो भी एनर्जी देंगे, ओके, वो एनर्जी कहाँ स्टोर होगी? Okay, in their degree of freedom. Okay, so energy is stored. Okay, so what is equipartition law says that energy will be equally distributed or stored, equally distributed, okay, among all the degree of freedom. Okay, degree of freedom. Okay, so now हम बात कर रहे हैं क्रिस्टल की. Okay, this is my crystal. Okay, so I told you we can represent crystal by harmonic oscillators. Okay, so there we have springs. Okay, so this is two-dimensional representation of a crystal. Okay, so I'm talking about three-dimensional crystal. So these are my atoms. Okay, so this is my crystal. Okay, now what happens whenever I give my energy to system? Okay, so it can do three things. Okay, either it can be stored in translation motion, okay, translation degree of freedom, or rotational degree of freedom, or in vibrational degree of freedom. Correct? If I give energy to system, okay, degree of freedom का मतलब क्या है कि ट्रांसलेशन की डिग्री ऑफ फ्रीडम कितनी है, रोटेशनल की डिग्री ऑफ फ्रीडम कितनी है, वाइब्रेशन की डिग्री ऑफ फ्रीडम कितनी है. सो इन द केस ऑफ लैटिस क्रिस्टल, ओके, व्हाटएवर एनर्जी विल सप्लाई टू द सिस्टम, दैट विल बी स्टोर ओनली इज वाइब्रेशनल डिग्री ऑफ फ्रीडम्स. ओके, क्योंकि ये जो क्रिस्टल है, जो एटम से ट्रांसलेट होते नहीं है, पूरा क्रिस्टल ट्रांसलेट होता नहीं है. ओके, एज एवरेज. ओके, ना ही इसमें रोटेशन हो रहा है इफ इट इज मोनो एटॉमिक क्रिस्टल. सो व्हाटएवर एनर्जी विल गिव, ओके, दैट विल बी स्टोर्ड in their vibrational degree of freedoms. Okay, so what are the main assumption of this model? First assumption is based on this model is based on equipartition law of energy. Okay, second thing is it considers, okay, each atom as a 3D harmonic oscillator. 3D harmonic oscillator. Okay, okay, and 3D harmonic oscillator क्या होता है? Okay, a 3D harmonic oscillator, is equivalent to three linear harmonic oscillator, Okay, now suppose
यहाँ हम ऊपर बोल रहे हैं कि इक्विपार्टीशन ऑफ एनर्जी वो ये कर रहे हैं, फॉलो कर रहे हैं.
हाँ.
मतलब सब मोड्स को एनर्जी सेम होगी, ट्रांसलेशनल, वाइब्रेशनल एंड एवरीथिंग.
हाँ,
और ऐसे ही है ना. और
पर यहाँ पे ट्रांसलेशन और रोटेशनल तो है ही नहीं. ओके,
हाँ सर,
तो जो भी एनर्जी दे रहे हैं वो वाइब्रेशनल मोड्स में ओनली स्टोर हो रहा है. ठीक है.
ओके, तब मैं इक्विपार्टीशन एनर्जी कैसे वो फॉलो करेगा ना?
जो भी एनर्जी जो मोड है जो होगा उसी में तो स्टोर होगा. जो मोड है ही नहीं उसमें कहां से स्टोर होगा? तो जितनी डिग्री ऑफ फ्रीडम होगी उसमें इक्वली डिस्ट्रीब्यूट होगा, हाफ के टी पर मोड में. ओके, पर डिग्री ऑफ फ्रीडम द एनर्जी इज हाफ के टी. तो जितनी डिग्री ऑफ फ्रीडम होगी सब में हाफ के टी चला जाएगा. अब इसमें खाली हमारे पास वाइब्रेशनली मोशन है, तो जितना भी एनर्जी जाएगा वो वाइब्रेशनल काइनेटिक एनर्जी और वाइब्रेशनल पोटेंशियल एनर्जी में जाएगा. Okay, so now suppose if I want to calculate the energy of one more assumption is that all the atoms are vibrating. All the atoms are vibrating, okay, independently. This model assumes, okay. Now suppose I have a crystal, okay.
I have a question.
Uh,
Does equipartition means, I mean, there are 3 degrees of vibration, right? I mean, it can vibrate along X, Y, or Z axis.
yes.
Does this equipartition means the amplitude of oscillation along all those 3 directions will be equal?
Yeah. So what I can write, suppose if it's a one dimensional oscillator, okay. So what is this energy? It will have a what, kinetic energy 2 by px square, okay. Suppose the x direction, it's x direction, okay. So
Yes, sir.
okay, similarly it will have a potential energy half k y square, half kx square,
X
okay.
square, yes.
Okay, so now, so what is the meaning of degree of freedom? Okay, तो आपके एनर्जी एक्सप्रेशन में जितनी भी क्वाड्रेटिक टर्म्स होती हैं, ओके, आपका whenever you write your energy expression, उसमें जितनी भी क्वाड्रेटिक टर्म्स होती है वो आपकी डिग्री ऑफ फ्रीडम होती है, ओके. सो फॉर एग्जांपल हियर वन, अगर मुझे इसकी 1D हार्मोनिक ऑसिलेटर की काइनेटिक एनर्जी निकालनी है, तो इसमें 2 डिग्री ऑफ फ्रीडम में, ये एक डिग्री ऑफ फ्रीडम, एक डिग्री ऑफ फ्रीडम, और हर डिग्री ऑफ फ्रीडम में जो एनर्जी होगी वो होगी हाफ kT plus half kT, okay. That
so
means
all total there will be 6 degrees of freedom.
yes, okay. So यहाँ पर क्या हो जाएगा, आपकी जो एवरेज एनर्जी है वो 1D हार्मोनिक ऑसिलेटर की, that is kT, okay. You might have calculated this in thermodynamics statistical course, okay. So classically the average energy of harmonic oscillator is one dimension is kT, okay. Now you have 3D harmonic oscillator, okay. So 3D harmonic क्या होगा, if I write the energy expression, okay, so we have a x term px square, okay, half py square, okay, half 2m pz square, okay, half kx square plus half ky square plus half kz square, okay. So यहाँ पर हमारे पास में 6 terms हैं, okay. So that means we have 6 degree of freedoms, okay. That means now my energy, okay, my energy of, and the energy total, the average energy of oscillator will be what, how much? That will be your 6 into half kT, okay. So this will become how much? 3 kT, okay. Now if I am talking about molar specific heat, okay, so molar specific heat मतलब क्या हो जाएगा, total energy, तो total vibration energy कितना हो जाएगा, total vibration energy of solid, total vibrational energy of solid, okay, per mole, okay. ये कितना हो जाएगा, Na into E. Na एक मोल में अवोगाड्रो नंबर के एटम्स हैं, okay. So what become, this become what, 3Na kT. And if I want to calculate what specific heat CV, that will be what, dE by dt at constant volume, and that will give me 3Na k, which is equal to 3R, okay, which is roughly equal to 5.96 or 5.96 calorie per Kelvin per mole, okay. So this is your classical model, okay. So classical model again only it says that the specific case of solid is constant, which is equal to 3R, okay. So which is true only at higher temperature. So this model fails to explain the behavior of specific heat at lower temperatures, okay. So now so this model is clear, na?
Yes, sir.
Okay. So now, so here we have treated our atom as a classical harmonic oscillator, okay. Now we are going to the second model, which is your Einstein model. So what is Einstein model says, okay. What are the assumption of Einstein model, okay. So put the heading Einstein model. So Einstein model is basically treats your oscillator quantum mechanically, okay. So it gives quantum mechanical treatment, okay, quantum mechanical treatment, okay. So what are the main assumption of this model? Number one, okay, it says all atoms vibrate with same frequency, okay, same omega 0, same frequency omega 0, okay. And now because it says it is a, since it is a treating at harmonic oscillator as a quantum mechanically, so energy of oscillator we know quantum mechanically is given by what, क्या एनर्जी होती है, n+1 half h cut omega, okay, where n is what, 0, 1, 2, 3, so on, okay. And the frequency of all the atoms are same, so I'm taking the frequency is omega naught, okay. So what is this is, if you put 0, it will give me what, 0 point energy. 0 point energy will be half h cut omega, okay. Now when I'm treating I'm calculating specific heat, okay, I can leave this 0 point energy because finally मुझे क्या करना, differentiate करना है ना. Finally I will differentiate this expression. If I have total energy, I will differentiate that energy with respect to t, okay. तो ये वैसे भी cancel हो जाएगा, okay. So now if you want you can take this expression also, okay. There will be slight change in the final expression, okay. Specific it will be same, only total energy of the system will change if I take this expression or if I take this expression, okay. En equals to n h cut omega naught, okay. So I am taking the energy of oscillator as a n h cut omega, okay, where n is I already defined 0, 1, 2, 3, okay. Is this point clear? Agar the exact expression is this one, okay. If I use this expression and this expression, my specific heat value will be same, okay. Only difference will come in what, internal energy. We'll see that one, okay. So I am using now expression this one, okay. You have to use this expression as a homework, okay. So now the number one assumption is,
Sir, what is the homework?
Homework. So I am taking the energy En of oscillator as a n h cut omega naught, okay. You have to take this expression and you have to derive this expression for specific heat, what I'm going to derive now, okay. You have to follow same sequence, only you have to replace the expression of energy by this. Clear?
Yes, sir.
Okay. So now I'm taking the energy of harmonic oscillator as, okay, En equals to n h cut omega naught, okay. So if I draw this energy, okay, what will happen? This will be 0, h cut omega, 2 h cut omega, okay, and so on. This will be n h cut omega, okay. And difference between the two level is what? H cut omega, okay. And now if I want to write the number of oscillator, okay, at each energy state, okay, the number of oscillator at each energy state, okay, that will be given by Boltzmann equation, Boltzmann distribution function Nn, okay. The number of oscillator at nth energy level, that will be given by what, n0 exponential minus En upon, okay, minus En upon kt, okay. Where n, what is n0? What is n0?
Total number of particles.
No, and n0 is the number of atom
in ground state
at, okay, at E is equal to 0, okay, 0 at 0 energy level, okay, at 0 point energy level, 0 energy level, okay. ये बोल्ट्जमैन स्टैटिस्टिक्स क्या है ना, दो सिस्टम में डिफरेंस ये है, ओके. तो हम कैसे निकालते हैं, एक्सपोनेंशियल माइनस E2 माइनस E1 अपॉन KT, ऐसे तो निकालते हैं मैक्सवेल बोल्ट्जमैन स्टैटिक्स. अगर मुझे नंबर चाहिए, ओके, अगर लेवल 2 में नंबर चाहिए, सो इफ आई वांट n2 by n1, So we use this Boltzmann statics. Okay. So here, if I want to use, okay, if I want to calculate the number of oscillator in nth energy state, I can use this Boltzmann statics. Okay. Now my aim is what? My aim is to calculate average energy. Okay. So average energy is what? I can take nth atom, number of atom nn, okay, their energy En divided by total number nn. Okay, when n is where n varies from what? N varies from 0 to infinite. Okay, 0 to infinite. Can I write like this?
Yes, sir.
Okay.
You're finding average energy now.
Average energy. Okay. So now if I, so average energy क्या है? एक energy level पे कितने atoms हैं? ऐसे करके मैंने total energy निकाल लिया. Total energy को total particles से divide कर दिया. Okay, तो average energy आ गया मेरे पास में. Okay, so now what is average energy? E. Okay, so this will be n equals to 0 to infinite. Okay, nn is what? Nn is n0 exponential minus En kt into En. Okay, and this will be what? N is equal to 0 infinite. Okay, and n is what? N0 exponential minus En by kt. Okay, so अब मैं क्या n0 कॉमन ले लेता हूं. I can cut it. I can take n0 as a common. Okay, so now my average energy क्या आ जाएगा? यहाँ से मैंने n0 कॉमन है, साइड टर्म से बाहर निकाल देंगे, कॉमन है तो कट जाएगा. ओके, सो नाउ आई हैव एक्सप्रेशन. ओके, En e power minus En is again what? N h cut omega naught e. Okay, En by kt. So n h cut omega naught upon kt. Okay, और नीचे क्या आ जाएगा? नीचे अगेन summation e power minus n h cut omega naught kt. And n varies from what? 0 to infinite. यहाँ तक क्लियर है?
Yes, sir.
ओके, आगे चलें. So now if we solve it further, okay, what we can write? So we can write now nh. So we have to give the values to n. Okay, so if I give values to n, okay, so let your x is equal to minus, okay, h naught omega kt. Okay, so so you can write now this expression as n is equal to 0 infinite and okay, h cut omega naught e power minus nx, okay, upon n0 infinite e power minus x nx. Okay, can I write like this?
Yes.
Okay, now you can solve it further. Okay, so h cut omega naught. Okay, now I'm giving values. When it's 0, I'll 0. If I give 1, okay, so I'll get e power x. Okay, sorry, nx, because I took minus here. Okay, so this is nx. So this will be ex. Okay, if I put 2, okay, so this will be 2 e power 2 ex. इसको मैंने बाहर निकाल दिया है. Okay, so this will be 3 e power 3x. Okay, and so on. Similarly, अगर मुझे नीचे लिखना है, so this I can write as put 0. Okay, I'll get 1. Then if I put 1 e power x, okay, e power 2x plus e power 3x, so on. ये क्लियर है यहां तक? अब इसको कैसे लिख सकते, इसको कैसे लिख सकते हैं? So I can write now this expression as average kinetic energy, okay, h cut omega d by dx log of 1 plus ex e power 2x plus e power 3x so on. इस इक्वेशन को ऐसे लिख सकते हैं क्या?
Yes, sir.
ओके, सो अगर इसको आप डिफरेंशिएट करोगे तो 1/x ये आ जाएगा, फिर इसको अगर वापस डिफरेंशिएट करोगे तो 1 का 0, x का क्या आ जाएगा, x आ जाएगा, e टू पावर का 2 e पावर 2x आ जाएगा, 3 e पावर 3x आ जाएगा. सो वी कैन राइट लाइक दिस. ओके, नाउ differentiate this equation. So h cut omega, if I differentiate, okay, what I'll get so d by dx log. Okay, now this is an infinite series which I can write as what, the first term is 1, so I can write 1 minus r. 1 minus r is what, e power x. Can I write like this?
Yes.
Yes, sir.
Okay, so now differentiate this equation. Okay, so if I differentiate this equation, this will give me what, h cut omega, okay, d by dx of log 1 by x. Okay, so that will give me 1 minus e power x. Again I differentiate 1 upon 1 minus ex, that will give me minus 1 upon 1 minus ex power square. Okay, and again if I differentiate this term, this will give me minus e power x. Okay, so minus become positive, h cut omega. Okay, one term remaining here, so I got ex upon 1 minus ex. Okay, and that I can write h cut omega. Okay, and that I can write e power minus x plus 1. Okay, now I know what is x. X is what, h cut minus h. हाँ बोलिए.
Say in differentiation log 1 upon 1 minus e to power x का 1 minus e to power x, फिर you will differentiate.
वन
ये -1 आएगा ना
कौन सा?
नीचे एकदम लास्ट लाइन.
ये लास्ट में ये वाला नहीं, माइनस प्लस हो गया ना, माइनस प्लस हो गया, यहाँ का भी माइनस आएगा ना एक, जिसको डिफरेंशिएट करेंगे 1 माइनस एक्स को तो भी तो माइनस आएगा एक.
या इट
प्लस ओमेगा नॉट है ना, वो
ओमेगा नॉट है,
ओमेगा नॉट है ना.
ओमेगा नॉट है. ओके,
हाँ वो ठीक है, पर लास्ट लाइन में हम बस e to the power x से डिवाइड कर रहे हैं ना.
हाँ डिवाइड कर दिया, इसको नीचे डिवाइड कर दिया,
तो माइनस था.
तो ये माइनस हो गया, ये माइनस था.
हाँ फिर -1 होगा ना.
-1, करेक्ट, दिस इज ओके. ओके, यस, ओके, दिस इज करेक्ट. ओके,
और
सो नाउ
यहाँ पे एक और assumption है, right? I mean we can write this formula 1 by 1 minus r when r mod r is less than 1. So we are assuming e to the power x is less than 1.
so this is already less than 1 na? What is x? Okay, e power x is what, minus na? This minus h naught omega kt.
Yeah,
So
that has to be less than 1.
so if I take the graph of this one, okay, e power x, okay, वो कैसा रहता है, ऐसे नहीं आता क्या?
Okay, sorry.
तो 1 के नीचे नहीं आ गया. Okay,
Yeah.
so this will become now, this become now my average energy. Okay, my average energy become what, h omega. Okay, that become h cut naught by kt. Okay, -1. Okay, so this is my average energy. Okay, average energy of a harmonic oscillator. Okay, now I want total energy. तो कैसे निकलेगा total energy, कैसे निकलेगा? If I want total energy, okay, so I want to calculate molar specific heat, so I have to multiply. Okay, so one harmonic oscillator is equal to three harmonic oscillators. Okay, so total energy will be what, 3 Na E. Okay, that will be 3 Na h cut omega. Okay, E h cut omega naught by kt -1. Okay, so this is my total energy. अगर मैं जो मैंने एक्सप्रेशन लिया शुरू में, अगर इफ आई यूज दिस एक्सप्रेशन, एनर्जी इक्वल्स टू n प्लस हाफ h का ओमेगा. ओके, सो तो मेरा जो एवरेज एनर्जी आएगा, ये आई विल गेट वन मोर टर्म, h का ओमेगा नॉट.
कहीं पे इंफिनिट नहीं आएगा. किधर भी इंफिनिट नहीं हो जाएगा वो वहां पे इस बार ओमेगा के लिए. अगर आप
ये पार्टीशन फंक्शन यूज कर रहे हो, ये वाला एक्सप्रेशन यूज कर रहे हो एनर्जी का, तो आप में इसमें यहाँ खाली 0 पर एनर्जी जुड़ जाएगी. ओके, वो मैंने आपको होमवर्क दिया है, आप ट्राई करके देखना उसको. ठीक है.
ओके सर.
सो नाउ वी हैव टू, आवर एम इज टू कैलकुलेट स्पेसिफिक हीट. So specific heat कैसे calculate करेंगे? Differentiate this expression. Okay, so I have to calculate a specific heat CV. Okay, that will be dE by dt. Okay, so differentiate this equation. Okay, so what will it give? It will give me dE dt at constant volume. So this will give me around 3 Na kb, 3 Na kb h cut nu upon kt square. Okay, square E h cut omega by kbt. Okay, h cut omega ko you can write h nu also. Okay, you can write h nu also. kbt upon E h cut omega kbt minus 1 का square. Okay, so सिंपल है. इसको करेंगे तो क्या आएगा? इसको स्क्वायर, फिर इसका एक्सप्रेशन करेंगे तो ये वाला. ओके, फिर क्या करेंगे हम लोग? टी को करेंगे तो माइनस 1/t स्क्वायर आएगा. ओके, और इसका एक माइनस आएगा, माइनस प्लस प्लस हो जाएगा, और केबी से मल्टीप्लाई कर दिया हमने तो ये हमारा स्क्वायर बन गया. चेक करो सही कि नहीं है. दिस इज माय एनर्जी. यस सर. बाकी लोग का भी आ रहा है. Okay, so this is my expression for specific heat. Okay, now I want to check the this expression in the limit of high temperature and low temperature. Okay, so in high temperature range. Okay, so so we have seen my energy. Okay, equipartition and the average energy of oscillator, which was equal to h cut omega naught. Okay, e power h cut omega naught by kt minus 1. Okay, so for multiplying by this, it will come your total energy, and you differentiate that one, that will be specific heat. So I'm solving this expression for high temperature range. Okay, so at high temperature range, what will become? This quantity become very less. Okay, so I can write e power x is equal to 1 plus x. Okay, so I can write this one as h cut omega. Okay, so this will become 1 plus h cut omega naught by kt. Okay, minus 1. Okay, so 1 से 1 cancel हो गया, ये भी cancel हो गया. So that now average energy of a quantum harmonic oscillator, okay, at high temperature is kt. So वही result आ गया जो हमारे पास आया था पहले क्लासिकल में. So that means at high temperature your quantum mechanics, okay, अगर high temperature limit लगाओगे तो you get your classical results. Okay, low pressure and high temperature पे. हाँ
सर, ये e to power x को आपने एक्सपेंड किया हाई टेम्परेचर पे.
हाँ, 1 plus x, 1 plus x, 1 plus x, 1 plus x. Okay, so 1
सर why, मतलब how you think that, मतलब
भी टेम्परेचर अगर हाई है तो ये टर्म लो नहीं हो जाएगी.
yes sir, low हो जाएगा.
So other time I'm neglecting. Okay, higher times I'm neglecting.
Okay sir.
So again you're getting this kt. Okay, so this will give you total energy. What? This will give you 3 Na kt kbt. Okay, and if you differentiate you get cv d dt. Okay, at constant volume that will give you 3 Na kb. Okay, that is 3r. So at low temperature, okay, at high temperature, this model also explain your specific heats. Okay, now that classical model also was saying that, suggesting that the specific heats of all solids at all temperatures is constant. Okay, now this also says at high temperature your specific heat is equal to 3r, which is our experimental observation. Okay, now what we want to see at lower थ्री डायमेंशनल में लिया ना, एन एटम है. ओके, और हर एटम थ्री डायमेंशनल है, तो हर एटम को हमने 3D वन 3D हार्मोनिक ऑसिलेटर्स इक्विवेलेंट टू 3 लीनियर हार्मोनिक ऑसिलेटर्स. ओके,
सर मतलब हाई टेम्परेचर पे क्लासिकल और आइंस्टाइन दोनों बोल रहे हैं CV इक्वल्स टू 3r.
यस यस.
बट एट लो टेम्परेचर्स,
तो अभी तो लो टेम्परेचर रेंज पे कैलकुलेट करो. ओके, सो नाउ वी आर पुटिंग द रेंज. ओके, low temperature range. Okay, low temperature range.
So we can neglect the -1, right?
Okay, so at low temperature range, okay, we have our average energy. This is the average energy E. Okay, h cut omega. Okay, E h cut omega naught kt -1. If this is a lower temperature, okay, so we can neglect this one in comparison to this exponential terms. Okay, correct. So as you said, it is correct. Okay, so we can neglect as at low temperature. Okay, your E h naught by kt is greater than 1. Okay, so I can write my energy as h cut omega naught. Okay, so this will become exponential minus h naught v upon kt. Okay, and total energy will be n. Total energy E will be 3 na. Okay, h cut omega e power h cut omega naught by kt. Okay, and when you differentiate, okay, so what we'll get if you differentiate? So what we'll get if you differentiate? So if I want, okay, cv d by dt, okay, at constant volume, okay, so this will give you 3 na, okay, h cut omega naught. Okay, if you differentiate this one, this will come minus h cut omega naught by kt, minus will come. Okay, and minus when you differentiate this term, again h naught omega to kt, one minus will come, that will come positive. Okay, so again it will come h naught kb. Okay, and I can make it a square, and I can multiply this term na by kb. Okay, so this will come 3 kt also come kt. Okay, so 3 na kb h cut omega naught by kbt square. Okay, e power exponential minus h cut omega by kt. Okay, and I can define a temperature, Einstein temperature theta e, which is equal to h cut omega naught upon kb. Okay, so I can write this equation as 3 na kb. Okay, this will be theta e upon t square e power minus theta e by t. Okay, so now you can see at lower temperature, okay, if this temperature is low, okay, so this will become almost infinite, so c will be 0. So this model also explains, okay, that at higher temperature, if you plot this as a theta e by t, okay, t by theta e, okay, t by theta e, so this model also, एक minute, this also gives you a, at high temperature you have a specific heat equal to 3R. Okay, but at load and at t is equal to 0 also you have 0 CV. If t is equal to 0, this become infinite, you see this become minus infinite, and this becomes 0. So t is equal to 0 also, this explains the specific heat. Okay, only lower regions, okay, it says your specific heat is proportional to what? Minus theta e by t, exponential dependence. Okay, exponential, there's exponential dependence of temperature with temperature
By t squared, right?
huh?
By t squared है ना?
t square नहीं है ये यहाँ पे ये exponential term dominate करेगी. Okay, okay,
so
this
higher temperatures पे तो ये exponential term 1 हो जा रहा है.
हाँ, हाई टेम्परेचर पे तो हम देखा ना, ये अगर इसको इनफाइनाइट कर दिए तो ये पावर खत्म हो जाएगा. ठीक है,
0 हो रहा है.
तो CV is proportional to theta c upon t का square.
नहीं वो तो ये तो अलग एक्सप्रेशन है, तो ये तो हमने ऑलरेडी निकाला है, मेन एक्सप्रेशन में देखना पड़ेगा. हमने देखा ना कांस्टेंट आया था. ओके, हाई टेम्परेचर पे,
इसको बस लो टेम्परेचर पे
ये लो टेम्परेचर एक्सप्रेशन. ओके, okay, so here also it says that specific heat decreases with temperature, but the decrease very fast. Okay, so we are not getting that CV equal to TQ by law. Okay, so this is experimental law. Okay, that your CV decreases the temperature as a power of Q, but here it's decreasing as a power, it is decreasing more faster than this law. Okay, so at low temperature, again this model is unable to explain, okay, the specific heats. Okay, so here I would define your this temperature, this your theta E. Okay, theta is what? Your Einstein temperature.
So Einstein theory basically explained very low temperatures and very high temperatures.
हाँ, अभी डीप वेरी लो पे क्या हो रहा है? वेरी लो पे
जीरो
ये
की
बस
तरफ जा रहा है।
जीरो तो जा रहा है, वेरी लो पे ये बस शार्प डिक्रीज होता है।
हाँ,
ओके,
बहुत शार्प।
और एक्सपेरिमेंटली क्या होता है? टी क्यूब की तरह डिक्रीज होना चाहिए, वेरी लो टेम्परेचर। ओके, हाई टेम्परेचर पे तो ये कांस्टेंट है, दे ही रहा है। इंटरमीडिएट पे तो आप सेम मान सकते हो, टी क्यू मान रहे हो या ये मान रहे हो, उसमें सेम है। इंटरमीडिएट टेम्परेचर पे तो ऑलमोस्ट ज्यादा डिफरेंस नहीं है। तो जैसे ही हम जाएंगे बिलो 77 के, ओके, अगर सपोज सुपर कंडक्टिंग ट्रांजिशन हो रहा है तो और फास्ट गिरेगा। ओके, तो बिकॉज इफ यू टेकिंग मेटल की स्पेसिफिक हीट, यहाँ तो अगर इंसुलेटर है तो इंसुलेटर की जो स्पेसिफिक हीट है खाली लेटेस्ट वाइब्रेशन पे डिपेंड करती है, बट इफ इट इज अ मेटल देन देयर इज अ कंट्रीब्यूशन फ्रॉम इलेक्ट्रॉन आल्सो। ओके, व्हाटएवर एनर्जी वी आर गिविंग, दैट एनर्जी विल बी टेकन बाय इलेक्ट्रॉन आल्सो। ओके, यहाँ पे तो जो भी एनर्जी दे रहे हैं वो खाली लेटेस्ट वाइब्रेशन में कन्वर्ट हो रही है। So they are at low temperature, the specific heat proportional to temperature T also. That's why if you take metal, okay, at very low temperature, metal specific heat is given by what? AT plus BT cube. ऐसा एक्सप्रेशन देखा कभी? देखा होगा ना? तो वो मेटल के लिए इलेक्ट्रॉन का कंट्रीब्यूशन लग जाएगा, वो देखेंगे जब फ्री इलेक्ट्रॉन थ्योरी देखेंगे। ओके, तो दिस वाज योर आइंस्टाइन मॉडल। ओके, हाँ, सो फॉर एग्जांपल, हाँ बोलिए।
ये जो अभी हमने फाइंड आउट किया है सीवी, वो लो टेम्परेचर के लिए।
अब ये एक्सप्रेशन निकाला वो लो टेम्परेचर के लिए, लो टेम्परेचर रेंज के लिए।
ओके, और आपने जब बताया लो टेम्परेचर होगा तो कौन सी टर्म, वो समझ में नहीं आ रहा वो जो बोल रहे हो।
लो टेम्परेचर पे ये एक्चुअली आपको जो एक्सपेरिमेंटल कर्व है वो बोलता है कि आपका जो स्पेसिफिक हीट है वो टी क्यूब लॉ फॉलो करना चाहिए, पर यहाँ पे क्या एक्सपोनेंशियल टर्म डोमिनेट कर रही है ना लो टेम्परेचर पे। क्लियर?
हाँ सर।
तो ये जो मॉडल है, ये लो टेम्परेचर पे जो फास्ट डिक्रीज है बिलो 77 केल्विन। ओके, जो लो टेम्परेचर, जितना टेम्परेचर लो होगा जितना टेम्परेचर लो होगा उतना ही फास्ट ये ड्रॉप होगा। ओके, तो लो टेम्परेचर पे ये जो फास्ट डिक्रीज हो रहा है, that is not agreement with the experimental observation. That's what I'm saying. Okay, so now if you take theta E Einstein model, okay, Einstein is temperature. Okay, this is for silver. If we take this exam is for silver, this value is 200 to 300. Okay, so of course theta E is what? Theta E is what? H cut omega naught upon K. Okay, so it depends on omega. Omega is that frequency. Okay, and we have seen in the first class omega naught is what? 4 beta by m. Okay, this is maximum, it's not maximum. So it depends on what? Depends on your crystal, depends on your crystal force. Metal and metal is a what? Metallic bonding. So generally this beta is less for silver. Okay, so for silver we get theta equal to 200 to 300 values. Okay, so if I take room temperature Kelvin, if I take room temperature कितना होता है room temperature? 300 Kelvin. So around room temperature, if I take room temperature then or slightly above the room temperature, okay, I will come on what? Higher temperature region. So if my T, if room temperature, my T will be greater than theta E. Okay, so at room temperature itself I am getting this 3R values. Okay, and similarly if I take diamond, this is for silver. Similarly if I take diamond, okay, theta E value is around 320 Kelvin. Okay, why? Because now in the case of diamond, okay, we have covalent bonds. Okay, so your beta, this beta is very high, so this frequency, okay, this frequency is very high for your diamond. Okay, so if frequency is high, that means this energy is very high. If I want to so if I want to make it more than kT, okay, so I have so if I want to make more than kT, I have to increase temperature more. Okay, ये पॉइंट क्लियर है? बी केटी जैसे सिल्वर है, ओके, सिल्वर के लिए जो ओमेगा नॉट है दैट इज लेस। ओके, सो रूम टेम्परेचर इटसेल्फ पे क्या होता है? केटी क्या होता है? आपके एच कॉट ओमेगा से ज्यादा हो जाता है। ये कम है, इसको इसको कैलकुलेट करेंगे सिल्वर के लिए, तो रूम टेम्परेचर पे इटसेल्फ केटी ज्यादा है, ओके। बट इफ आई टेक for this term for diamond, okay, at room temperature T ज्यादा है रूम टेम्परेचर पे। if I want to make this term more, okay, I have to increase the temperature KT। तो हायर टेम्परेचर पे ही जाके ये इस टर्म से ज्यादा होगा, और जब ये इससे ज्यादा होगा तभी तभी ये वाला कर्व फॉलो होगा, तभी ये कांस्टेंट होगा। हायर टेम्परेचर का मतलब क्या है? हायर टेम्परेचर का मतलब है आपका जो टेम्परेचर T शुड बी ग्रेटर देन थीटा ई, ओके। तो यहाँ पर तो T ये जो है, जो थीटा ई है वो इटसेल्फ रूम टेम्परेचर से कम ही है, ओके, तो ऑटोमेटिकली ज्यादा है। सो फॉर इन द केस ऑफ डायमंड, ओके, this constant curve will come at higher T, okay। तो जो सिल्वर के लिए हमको 200 केल्विन हमको जो रूम टेम्परेचर मिल जा रहा है, वही फिनोमिना 3R CV equal to 3R will get for diamond at temperature of 320 degree Kelvin, more than 320 degree Kelvins, okay। क्लियर है? क्योंकि you have a covalent bond, strong bonds in that case of diamond, okay। So the beta value is very high, so the natural frequency vibration of diamond is very high compared to silver.
So we
Sir.
can calculate the elastic constants also from this.
Elastic constant given होगा ना, elastic we should know the elastic constant, we can get theoretical values, okay।
Sir, at this temperature, can we break the bonds also?
अब देखना पड़ेगा बॉन्ड डिसोसिएशन एनर्जी कितना है, ओके। जनरली डायमंड तो बहुत स्टेबल होता है, ओके। So I have worked on graphites, okay। तो ग्रेफाइट पे हम we used to go up to 1200 टेम्परेचर। तो ग्रेफाइट पे तो डायमंड पे तो you can go up to 1800 centigrade, okay।
Graphite is more stable than diamond is more stable than graphite.
Yes, diamond is more stable, okay। चलो, I am stopping here. Tomorrow we'll start Debye model, okay।
Thank you,
sir.
Debye model will get the T cube.
Yes, tomorrow we'll see.
Good night, sir.
Good night.